Hello everyone. The title of this video is Using the Change of Base Formula for Logarithms. Now in this video, I'm going to be going over examples that are taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 6.5, called Logarithmic Properties. And I'm under the heading Using the Change of Base Formula for Logarithms. Each example I do will either be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section related to this particular objective. Alright, so before I actually get into examples here, I want to talk about what is this change of base formula. Now they have it written out here and a little proof of it, and also in this box here. Alright, so I'll read it out. I'll also write it and talk a little bit more about it. So if you're taking a logarithm base b of some number m, you can change this base b to any base you wish and write an equivalent expression with a log of that new base. So if you want the log base b of m, you can change base b to base n, take the log base n of m, but then you have to divide by the log base n of the original base to maintain equality. Alright, so I'll write that out again. So here's the change of base formula. That's right, change of base. So like I said, if you're taking a logarithm base b of some number, you can change the base to whatever other base you want. So say I change base b to base n, like they have in the paper there, log base n of m. Now that's not the end of it, right? You can't just change the base and say they're equal, right? For example, the log base 4 of 16, we know this is 2, right? 4 to the second power is 16. Say I decided to change the base 4 to a base 2, say that, just change log base 4 of 16 to log base 2 of 16. Well, log base 2 of 16 is 4, right? 2 to the fourth power is 16. So you see how they're not equal right yet? So I got to do something else, right? Just changing the base, right? These are not equal. So I can't just change the base to whatever I want and then leave it. After you change the base, you then must divide this new expression by another logarithm. Right? A logarithm with that same base you're changing it to, log base n, and the input of this denominator log is the original base. Right? The base started with base b. Alright, so sticking with the similar example I had here, the log base 4 of 16, right, we know that that's 2. If I change base 4 to base 2, say write the log base 2 of 16, I then have to divide by another logarithm base 2, and the input of this logarithm in the denominator is the original base. So divided by the log base 2 of 4. Log base 2 of 16 is 4. Log base 2 of 4 is 2. 4 divided by 2 equals 2. That works. That's true. So you can't just change the base to whatever you want. If you change the base to another base, you then have to divide by the log of the original base. That's the change of base formula. Alright. And we can also very easily see this. We can see more examples of this in the Desmos calculator. So I'll put in, y equals the log base b of x and add a slider for b. Just make sure b is some positive number. that's not 1 or 0. So like that, there's a log base 1.55. And then, beneath this, I'll put y equals, and then I'll change base b to base n, right? Log base n of x, and then make sure to divide by the log base n of the original base, which was b. All right, and I'll add a slider for n. And again, making sure that the n is a positive number that's not 0 or 1. All right, and now you see, when n is 2.4, b is 1.55, it doesn't really matter. Right? You can change b or n to whatever you want. The graphs are the same. See, when I turn one off and on, it's right on top of the other one. Say if, the original base is 5.3, I change it to a base of 4.05. They're still the same graph. Right? So those expressions are equivalent. Log base b of x and the log base n of x, divided by the log of the original base, log base n of b. Right? And a base that is commonly changed to is base 10 or base e, right? Those common logarithms or natural logarithms. And that's what we're going to do in a lot of these examples coming up. All right, so my first example, and my first set of examples, we're asked to use the change of base formula to evaluate. Right? Find the value of these logarithms and round to 5 decimal places, if necessary. All right. So the nearest 100,000th. Yeah, 5 decimal places, if needed, right? So here, the log base 5 of 3. 3 is not a nice power of 5, 5 to the 0 is 1. 5 to the first is 5. 5 to what power would be 3? Now, based on what I just told you, this should be 0 point something. Right? It's between 0 and 1. I know that much. So I'll start it off with 0 point blah. Now, you can, in most calculators nowadays, especially the Desmos, you can just punch in this expression as it is, and you'll get a value. What's the log base 5 of 3, and you see it's 0.682606, but the 5 decimal places, that would be 68261. Right? But we're not asked to just punch that in, right? We're asked to use the change of base formula. Because most calculators, right, a lot nowadays you can punch in whatever base you wish, but most basic calculators, basic scientific calculators, will have just a log button, log, log base 10, or an ln button, right, natural log, log base e. So if you had a calculator like that, and you wanted to figure out the log base 5 of 3, change it from base 5 to, say, base 10. So I say this is equal to the log base 10 of 3. Remember, you can't just change the base, right? Then after you change the base, you then have to divide by the log of that new base, with the input of the original base, the log of 5. Right? You could also say this is the natural log, log base e of 3. But then you got to divide by the natural log of 5, right? The natural log of the original base. Either one. It doesn't matter what base you change it to. As long as the input in the numerator is 3 and the input in the denominator log is 5, you'll get the same value. And we get approximately, and I'll show you, it doesn't matter which one you do. Right, like I said, you can do log base 10 of 3 divided by the log base 10 of the original base, 5, and it's the same value. Or natural log of 3, or log base e of 3 divided by the natural log of the original base, same value. I mean, I can change it to any base I want. Log base 7 of 3 divided by the log base 7 of 5, right, the original base. And this It's the same value every single time. You looking at this, right? 0.68261 if I'm rounding to 5 decimal places. But yeah, but typically you'll want to change it to base 10 or base e, right? Common logs or natural logs. Yeah, this rounded to 0.68261, rounded to 5 decimal places. Right, and again, remember what this means. This means 5 raised to this power should give me something that's around 3, because it's rounded. Okay. Now, the next example is something I shouldn't need a calculator for. I'll tell you what the value is right now. The base is a half, and 1/2 to what power would be 8. Well, we know a half to the third power would be 1/8, but this is the reciprocal of that, so I need a negative power, right? 1/2 to the negative 3. And there's no need to round that to 5 decimal places. 1/2 to the negative 3 power would be 8. Now say you didn't know that off the top of your head, or the decimals throw you off, or whatever, and you decide to go to a calculator. Use this change of base rule. So instead of log base half of 8, you decide to do log base 10 of 8 instead. But then you got to remember to, after you change the base, divide by the log of the original base, right? So if I were to enter this, you're going to see, or even do natural log, it doesn't matter. Do natural log base e of 8 divided by natural log, or log base e of 0.5. Again, whatever logs you're changing it to, whatever base you change it to, as long as the input in the numerator is 8 and the input in the denominator is 0.5, you'll end up with negative 3. And let's see that happen in my calculator here. Get rid of all this, and I'll just log of 8 divided by log of 0.5, and you see in negative 3, right, which is the log base 0.5 of 8. Right, same thing. Okay. Third example. Same question, same instructions. What's the log base 2 of 10? Right, 2 to what power would be 10? I can tell you right now, this is going to be 3 point something. This 2 to the third is 8, and 2 to the fourth is 16, right? And 10 is between 8 and 16. And yeah, if I change this to log base 10, the numerator is going to be 1, because the log base 10 of 10 is 1, and then divide by the log base 10 of 2, right? 1 divided by the log of 2. Or I could do natural log, right? Take the natural log of 10 and divide it by the natural log of 2. Either way, we're going to end up with the value that they're asking us for, and I'm going to round it to 5 decimal places. All right, so once again, I'll put in the, I'll do natural log of 10 divided by the natural log of 2, and like I said earlier, it was going to be 3 point something. It's 3.32193 if I round to the nearest, 100,000th, the 5 decimal places, 3.32193. 3.32193, and there we go. All right, and you can double check, take 2 to this power, and you should get a number that's close to 10. And again, it's close to 10, not actually 10, because it's rounded. And the fourth example, and again, it's all the same stuff. What's the log base 5 of 100? Now again, if you start going through your powers of 5, 5 squared is 25. 5 to the third would be 125, which is bigger than this. So the power I would need to raise 5 to is going to be 2 point something between 2 and 3. And I'll use change of base. This time I'm just going to go to base 10 this time. If I do log base 10 of 100, that's 2 in the numerator, right? That's the log base 10 of 100. divided by the log base 10 of 5. And that'll give me, my approximation. And I'm telling you, it should be 2 point something. So 2 divided by the log of 5. And yeah, 2.861353, so 35, right, if I'm rounding to the nearest 100,000th. So approximately 2.86135. And there we go. Right. And again, to double check it, 5 raised to this power should be close to 100, really, really, really close to 100. Okay, let's keep doing this. So 4 more of these, same procedure, right? What's the log base 3 of 22? Now 3 to the second power is 9. 3 to the third power is 27, which is too big, right? So it's between 2 and 3. Right? This is going to be about 2 point something. Go to my change the base rule. This time I'll use log base e. I'll do the natural log. So instead of log base 3, I do natural log of 22. But then make sure to divide by the natural log of the original base of 3. And this should give me the value they're asking for. So I'll go to my calculator. And I'll just do natural log of 22 divided by the natural log of the original base 3. And like I said, it's between 2 and 3. 2.813588, so 59. Right, if I'm going to 5, rounding to the nearest 100,000th. So approximately 2.81359. And again, if you want, take 3 raised to this power. Should be something really, really close to 22. Okay, log base 8 of 65. Now again, I know that 8 squared is 64. So this is a little more than 2. This is going to be 2 point something. And once again, I mean, just because it takes less writing, I'm going to do natural log. Just change from base 8 to base e. So natural log of 65. But then don't forget to divide by the natural log, or the log of the original base, 8. And that should give me the value they want. So I'm just going up here and changing 22 to 65 and 3 to 8. And you see 2.007455, so that would go up to 746. When I go to 5 decimal places, the nearest 100,000th, 2.00746. Again, you want to test it out. Take 8 raised to this power. Should get something really close to 65. All right. Here I have the log base 6 of 5.38. So 6 to what power is going to give me 5.38. Now I know that 6 to the first power is 6, which is too big. 6 to the 0 is 1, which is too small. So this is between 0 and 1. This is going to be 0 point something. And then again, I'll just use, now you can use log base 10, log base e, log base whatever you want. Just for shorter writing, I'm doing log base e every time now. So this is equivalent to the natural log of 5.38. And then don't forget, when you change the base, you then have to divide by the log of the original base, divided by the natural log of 6. And that should give me the value I wish for. So again, just changing this numerator input to 5.38 and the denominator to 6. And there you go. 0.93913 if I round to the nearest 100,000th. 93913, which I've written down here. Pardon me. And once again, you want to test it out. Take 6 to this power and see if it's close to 5.38, and it should be. this 8th example, log base 4 of 15 halves, right? If you write that as a decimal, that would be 7.5. So this is going to be about 1 point. This is between 1 and 2. Because 4 to the first is 4. 4 squared is 16. 7.5 is between those. And this is going to be the power we're raising 4 to is between 1 and 2. And again, I'm just going to change this to base e, natural log of 15 halves, and then divide that by the natural log of the original base 4, and that'll give me the value I'm looking for. Alright, so changing this input up here, I'm just going to write the decimal version, takes less typing. That's 15 halves, right, 7.5, and then the original base was 4. And yeah, it's 1.45345 if I'm rounding to the 5 decimal places. 1.45345. Right. And once again, change it to exponential form, see if it's close to true. It should be approximately true. 4 to this power should be close to 7.5. Wonderful. Alright, now my last few examples, my last page, is a different kind of problem, but you still may be asked something like this in the future. So suppose the log base 5 of 6 is the number a. Now you could find a value for this, punch this in a calculator, get a value, but let's just call it a. Whenever I see the log base 5 of 6, that's a. And the same thing for the log base 5 of 11. I know that you can punch this in a calculator to get a value, but let's just say whenever I see this, it's the number b. So we're asked to use the change of base formula along with properties of logarithms, remember the product rule, the quotient rule, the power rule, and so on, to rewrite each expression in terms of a and b. So I want to see some log base 5s of 6 and log base 5 of 11. Right? I want to see those in my rewriting of these expressions, so then we can replace those with a and b. For example, see how this is the log base 11 of 5, but both a and b are logs with base 5. So I use the change of base formula, change this to, instead of being base 11, I change it to base 5. So this is the log base 5 of 5. And remember, you can't just change the base. After you change the base, you then have to divide by this new log base 5 of the original base. And then we express this now, simplify it and express it in terms of a and b. Now the log base 5 of 5 is 1, right? 5 to the first power is 5. And then the log base 5 of 11, that's this. Remember, anytime you see the log base 5 of 11, that's going to be the number b. And this is what they're asking us for. Rewrite the expression, in terms of a and b. Well, there's an expression in terms of b. 1 divided by b. So I'm hoping that made sense, what was happening here, and this is going to be the case for the rest of these. Alright, so once again, this is log base 6. But both a and b were in base 5. So once again, I'm going to do change of base here. Rewrite this as a base 5 logarithm expression. So this is log base 5 of 55 divided by, and then the log base 5 of 6. Alright, there's your change of base rule. Now 55 is 5 times 11, right? It's a product. You can think of it as a product. So I can apply that product property up here and turn that into the log base 5 of 5 plus the log base 5 of 11. Remember, the log of a product is the sum of logarithms. Then the denominator is still the log base 5 of 6, and now I can totally simplify and write this in terms of a and b. In the numerator, I'm seeing the log base 5 of 5 again, that's just 1, plus, and then the log base 5 of 11, right, that was what we called b. So 1 plus b in the numerator, and then all this over, and the denominator has the log base 5 of 6, which is what we were asked to call a. So 1 plus b in the numerator, a in the denominator, and there's the expression simplified, rewritten in terms of a and b. Okay. All right, and I got just one more of these. So the same issue in the beginning. It's a log base 11, but these are in base 5. Or if I want to write it in terms of this a and b, I need things in base 5. So I use the change of base rule. So instead of the log base 11 of 6/11, I'll change it to the log base 11, or sorry, base 5. Right? I just said it. You want to change it to base 5 of 6/11 divided by the log base 5 of 11, right, of the original base. And then in the numerator, you see I have the log of a fraction, a quotient. I can apply that quotient rule. Make that the log base 5 of 6 minus the log base 5 of 11. And then that's all divided by the log base 5 of 11 still in the denominator. And now I have what I wanted, to rewrite this. Log base 5 of 6, remember that's called a. Minus, and then the log base 5 of 11, I'm seeing it twice here. Anywhere I see the log base 5 of 11, that's b. So I have a minus b in the numerator, and then b in the denominator. And if you actually divide both terms in the numerator by b, you'd have a divided by b minus 1. Either one of these is totally fine. Either one of these would be acceptable. So I'll put the word or in here. So this expression or this expression, either way, it's the original expression written in terms of a or a and b as they asked for. So I'm hoping that made sense, right? The use of the change of base rule and the product rule, the quotient rule were used here. And I was just trying to look for, trying to get the log base 5 of 6 to show up, and I was trying to get the log base 5 of 11 to show up so I could then replace them with a and b. You might see problems like this, of course, in the future. Alright, and that's all I got for you. I'm hoping that watching me go through these 11 examples here helps you in some way when you're asked to use the change of base formula for logarithms on your own. Thank you very much for watching.